Hello, and we're back with the last presentation of the day. Um, they say save the best for last. So here's the dessert. We have Seth Yap. He's a machine learning engineer at Nearmap, and he has spent the last 4 years working on systems to improve the training data available to vision models. Today, he's going to explain to us what is required to perform calibration at scale.
Right. Thank you for that introduction, Joaquin. And for everyone who's online watching, thank you for coming as well. If you're in the US, I know it's pretty late for you, so thank you for staying all the way for this talk. Now, today I'm going to be talking about how we implemented visual model calibration at scale at Nearmap. But before I do, let's just talk a bit about the Dunning-Kruger effect. So this is a bit of a digression, but in 1999, these two guys, David Dunning and Justin Kruger, published a paper which made this claim that confidence in one's abilities is not actually related to how often you are correct. Now, I've got bad news for you because it turns out that models can do it too. So in this graph, and I'm using the idea of accuracy a little bit loosely, you can see in the top right that the model is quite confident, but it's not quite as accurate to match. And in the bottom left, you can see the opposite, which is where the model is unconfident, but it actually gets things right more often than it thinks it does or it thinks it should. So, sorry, the gray line, the dashed line, that's actually where you want to be, and I'll explain why in just a minute. But what I'm going to do is talk through all these points. So if you're already familiar with calibration, the first section of this talk is going to be a breeze for you. I'm going to talk more about what calibration is, why we're doing it, and there's a few different calibration types, so I'll be talking about how they're different from each other. And then that's where the headline comes in, visual model calibration at scale. So in Nearmap's context, what exactly did we do, especially since we have 146 different classes in our latest model, and we used about 300,000 images in the calibration process. So like I said, there's different calibration types. We're looking at selecting different calibration types for different classes to get the best results. And with 146 classes, you can do that manually. So we had to do it in an automated manner. And then we also had to build in this explainability layer because we wanted to be able to double check that the results made sense. And then I'll just share some results that we had after calibrating the model. So let's just put things in context. Who is Nearmap and why are we interested in calibration? Well, we are a geospatial intelligence company that was founded in Perth, Western Australia in 2007. And we used to just sell photo maps. So what we used to tell people was, if you think of Google Maps, we are the more high resolution, more up-to-date version of that, which doesn't actually sound as great. But in 2020, that's when we started with our AI. So we were moving into the solution space, and we would run computer vision on all the imagery that we collected. And now actually every single survey that we fly has AI run on it. So we can tell you where the roads are, where the roofs are, where the solar panels, tennis courts, and swimming pools are. So you might have been able to tell from the images that have been in the slides so far that we do semantic segmentation, which means that for every single pixel in the photo map, we generate information about how many of the 146 classes in our latest model are present at that location. So why do we care about calibration? Calibration at its core is about aligning a model's confidence with how often a class is present. So if a model is 100% confident that a roof is present, then for all the 100% confidence predictions, I want a roof to actually be there in the pixel. If the model is 50% confident, then I want to see that the roof should be there about 50% of the time to match. That's what it means for a model to be well calibrated. So what else do you get from having a calibrated model? There's some downstream implications as well. It's got to do with how people use your data, right? So imagine you're calculating the likelihood that your roof will need to be replaced in the next year, and you have access to the model predictions. The results of your calculations are going to be based off of the confidence values that the model is giving you. And this is going to be a much more straightforward process if the model is calibrated, because the confidence values will now actually tell you the actual probability that your class is present. Now, the other reason why you might need calibrated models is that we specifically release a few different generations of AI contents. We're consistently making improvements to our model. And calibration just gives all these different release generations a common reference point and increases the stability of the systems which build on your predictions. All right. So what are our options for calibration? It's common to apply a sigmoid function to model logits. So one easy way to calibrate your model is simply to scale the sigmoid function. So this is the whole idea behind temperature scaling. We are basically performing a logistic regression. So this is the formula that you're going to be getting. What we're trying to find is the scale factor, that's S in the formula. And normally you can have a location parameter as well, but that is 0, so that's not part of the formula right here. When we talk about plat scaling, I'll be touching a bit more on the location parameter. So if you're using scikit-learn, what they do is they do this logistic regression with cross entropy loss. They add a little bit of regularization so you don't end up having too much of a slope, so that your scaling factor basically doesn't grow too large in magnitude. And then your fitted output function would look something like what's on the right. So instead of getting the gray dashes to link your logit values to the output, you would get the blue line. Plat scaling. So this is very similar to temperature scaling. One key difference now is that the location parameter can be non-zero. So this actually does have fairly significant implications, because assuming you're using the 0.5 mark, so in the middle of the graph, as the threshold for whether you say this class is present or not, temperature scaling, because it only scales your logits, it will not affect where that 0.5 threshold is. Whereas for plat scaling, it will. So it can actually affect your accuracy. Isotonic regression, what this tries to do is to fit a non-decreasing series of lines to the data. The implementation uses a mean squared error loss. So again, you just end up with all these steps that you can see on the right. And that's how it links your logits to your outputs. Up close, it looks like this. You can see the steps very clearly. But if you zoom out a little bit more, you might end up seeing something which, once again, approximates your logit, your sigmoid function. This isn't always a given. In this particular case that I ran, I believe it's an artifact of just the fact that when we did the original predictions, the activation function was the sigmoid function. So you're not going to end up with a calibration function that's drastically different from that. There will at least be some kind of similarity. Once again, this does not preserve your accuracy. Even though it's not easy to tell from this graph, the 0.5 mark can change as well. Spline calibration, it's a very similar idea, but you are fitting a cubic spline instead. You use a cross entropy loss, and then you add some regularization so that the spline becomes a bit smoother. So you actually penalize having too large of a second derivative for the spline. So any function will actually work for calibration. All these things are doing are changing how your model gets its prediction values compared to what the logits actually are. And if you do this right, you can get a better calibrated model without actually sacrificing on accuracy. So we use the first two options in our systems, temperature and plat scaling. And the last two methods that I've shown you are from external literature. So what did we do at Nearmap? We had to do this at scale. It gets slightly more complex. So to calibrate a model, you need the raw logits from the uncalibrated model to do the regressions that I was talking about. And this means, of course, that you need to run the uncalibrated model. So you have a model prediction step. At Nearmap, we already have a system for running separate apps in the pipeline. So this allows us to do things like run specific applications on a GPU and certain bits on a CPU. We use AWS, so you can pick your instance type based on what actually makes sense for you. Now, the full execution graph looks a bit like this, but what I actually want to focus on are the last two nodes in the bottom. And what we've essentially done is we've broken calibration into two steps. So one of them is an ETL extract, transform, and load step, and the actual calibration step. So what are we doing in the ETL step? Well, the reason we are doing this is that calibration is a very high input and output bound process. So the initial R&D code that we were developing would take 18 hours for a calibration run, and a large portion of it would just be spent pulling data. The reason for this is that for every single prediction that you're generating, you need to pair it up with a label. So you are pulling all your model predictions and you are pulling all your labels. The model also predicts all classes at once, whereas in calibration, what you care about is each class. So you're going to have to do some kind of transformation to split the classes up in the predictions anyway. And then again, the model predicts one set of predictions for all 146 classes for each image, whereas when you calibrate the model, what you really care is, hey, how is this class doing across an aggregation of all images? So again, just more transformation that you need to do. The ETL step also allows us to organize the data into separate splits, and I'll kind of talk about this later on. This becomes important when we do the automated calibration type selection. So how this ETL step works is we first have to generate a manifest of all the labeled areas that you're using in the calibration. We then divide the manifest out according to which split the data belongs to and which worker should process it. We have a means of doing a fan out step so that we do all the data pulling in parallel. This just basically gives us a lot of speed up. There is one optimization step that you want to do as well when you're, again, pulling data for 300,000 images at once. So between the fan step and the merge step, you have to offload your data to a data store, again, because each individual worker, we are fanning out across multiple nodes. This isn't just on a single node where we have multiple processes. It's just not fast enough. So in between, we're offloading our data to a data store. Again, we use AWS, so it's S3. And if you're going to store 300,000 individual images multiplied by 146 classes, it's prohibitively slow. As you know, input and output to S3 of many individual small objects is not a good idea. So what you do is you do a local merge first, where you just merge all the data that the worker extracted for each class together. So your data for, let's say, class number 0 would now be the data across all the images that that particular worker processed. And then when you do the global merge on your final node that's doing the final merge, you don't have to pull as many files, and it speeds things up quite a bit. Now, we have got a completely different set of challenges for calibration. So we have 146 classes and 3 different calibration options. So those are, we could go with temperature scaling, we could go with plat scaling, we could go with no calibration at all. And we can't actually manually go through every single class and pick a calibration type. Bearing in mind that we have multiple release candidates of a model before we actually launch the next generation of our AI product. So you would have to go through multiple rounds of calibration, quite possibly. There is also a lot of data to consider when you're comparing between calibration types. So you are going to have to narrow down your results into a set of simple rules that will let you pick the best type. And then we also have this constraint that we do not actually want calibration to decrease the accuracy of the model, because having a calibrated model that's less accurate than the uncalibrated model, that's not a good idea. So how do you actually measure how calibrated the model is? Because this is one of the deciding factors that we are going to want to look at. There's two ways. Expected calibration error is one of them. The maximum calibration error is also something you might want to consider, because the expected calibration error could go down, but you could end up with some results wherein, off cases, it's just very badly calibrated. So on the graph to the right, you can kind of see the calibration curve that I showed earlier. Now, how we get this is each data point corresponds to a histogram bin. So remember, each prediction is paired with a label. And that's how you actually can assign the predictions to different bins according to what the maximum value in each bin is and the minimum value is. So for example, if your bin is 0 to 0.1, all the predictions between 0 and 0.1 would fall in there. And this lets you calculate a number of things. One of them is the number of predictions in the bins. You can predict the mean prediction value, but you can also calculate the fraction of labels that correspond to the predictions in a bin which are positive. So again, the bin from 0 to 0.1, you have a whole bunch of predictions in there. You have all their paired labels. And maybe 90% of those labels are going to be positive. That's actually really bad if it's the 0 to 0.1 bin. So what you want to see is actually 10% of those labels being positive. That's your fraction of positive labels. Your expected calibration error is an expectation, so it's just a weighted average by the number of predictions in each bin. You just take the absolute value of your mean prediction value, subtract off the fraction of positive labels, and you do the weighted averaging. So once we've covered that, maximum calibration error is a lot easier to understand. It's literally just the maximum difference between your mean predicted value and fraction of positive labels across all the different bins. So this gives us our selection criteria. We take a conservative approach because we bias towards not calibrating. So we want to be very sure that calibration is not affecting anything else before we say that, hey, we're going to calibrate this. So this was one of the decisions that we made. So what we do is we have this priority order, right? And we only select a method that's from a lower priority if the expected calibration error, the maximum calibration error, and the F1 score are all better. So now that we have this, the calibration app looks a bit like this. Initialization, val step, graph generation and logging, sorting the calibration type. So that's where we do the selection test step, more logging, and then we finally upload the parameters. And I'll go through this in more detail in just a bit. So the initialization, what are we doing? Remember, we are generating the ECE, expected calibration error, maximum calibration error, and F1 scores for all the three different options, which are no calibration, temperature scaling, and plat scaling. And we're doing it across all classes. So we want to do this in parallel. So we have got some functors which can run in multiprocessing worker pools. We initialize that at the start. We've got a bunch of data loaders which know where to look in S3 for the data for the class that you want and for the split that you want. Again, I'll explain what the splits are later on, but it's related to why we have a val step and a test step. And then there's a class that handles all plotting that we set up as well. So the val and test steps are where the meat of the processing happens. As mentioned, we run the calibration on different splits. The stats calculations can be done independently. Sorry, so we run the calibration on the different types and classes independently, so we can parallelize that, and a lot of the score calculation can be parallelized as well. there's a bunch of stats that we need to calculate for graphing. That gets done. So these are going to be things like the bin counts, just so we can see, whether we had one bin with a lot more predictions than other bins. We calculate the F1 scores at various thresholds. We also calculate the first and third quartile values for the bins, in addition to just the mean predicted value, even though that doesn't come into play when we calculate our calibration error. But it does give us a sort of like sanity check. When we look at the graphs later, we can actually see, is there a huge difference in how the first quartile in the bin behaves versus the third quartile in the bin? There's a bunch of graphs which are also specific to each individual class, and these can be generated in the parallelized step as well. So I said I'll explain what the splits were. So the valve step is named after the validation split. So because we're doing automated calibration type selection, we need 3 separate splits of data. So we have the calibration split, the validation split, and the test split. We do all the regressions that happen in the calibration on the calibration split, and then we calculate the stats on the validation split. So this is how we end up selecting the calibration type, and then we run the actual calibration. We ran the stats calculation on the test split to get the final results. When we we print out the results that say like, hey, this is actually what our final calibration error is. Now the splits also give us the ability to do geographical partitioning. So we have to be quite deliberate about how we split our data as a geospatial intelligence company, because like one key example that I've used before is certain classes or certain predictions are highly geography dependent. So in the US, for example, 75% of homes or more have asphalt shingles. But if you're based in Australia, like I am, you're more likely to come across tile roofs. And that's exactly why you want to make sure that you have a good representation of each of these in your different splits. And then we have what I call the cross-class graphs. So these are the graphs which, again, for sanity checking, we pull in data across multiple classes. It gives you an overall view. We also have some extra processing where we extract the ECE, MCE, and F1 scores into a data frame. So what this does is it gives you a medium level of granularity between just looking at the final result, or we selected all these calibration types, and also just looking at the individual graphs itself. Like, you have the very high level overview, you have the very detailed way of doing things, but sometimes you just want a medium level sanity check. Again, we provide that as well. So having all the scores in one easy place will just let you compare, like, yes, indeed, this calibration type gave me better results on all of these metrics. Then we also filter out the invalid calibration types and perform the selection on whatever's valid. And we actually have this very handy thing, which is that in the logs, we provide a reason for the calibration type selection, which again is just yet another layer of sanity checking. So you can go into the logs and they'll be like, oh, we picked temperature scaling and we didn't pick plat scaling because plat scaling had a drop in your MCE value. And it's just a very easy way to understand what's going on. So we've covered up to the 4th step here, the sorting of the calibration types. The test step and its associated graphing are just mirroring what we do in the validation step. And then we have a registry. So in the last step, we are just uploading all the generated calibration parameters to the registry where we're storing everything. All right, so results. In our latest release, out of the 146 classes, we ended up with 23 classes having no calibration at all. 91 classes had temperature scaling applied to them, and 32 classes had plat scaling applied to them. And that actually makes sense if you consider that we were biased towards temperature scaling, again, because temperature scaling doesn't affect your accuracy. But it's also interesting to note that we actually did end up with a lot of classes where calibration actually improved things for the model. Now, the 23 classes that were not calibrated, these usually turned out to be classes where we didn't have a lot of data. So the calibration process, as expected, was a little bit noisy. So drilling a little bit deeper, if you remember the graph that I've been showing of the calibration curve, this was for our natural hard class. So what this predicts is natural style rocks and rock surfaces. And on the right side, this is what happens when we calibrated it. We picked temperature calibration, and you can see that the calibration curve now fits the ideal line a lot more closely. If you look at the images, that's the difference in the predictions between the uncalibrated and the calibrated model. So they actually look quite similar, but if you know what you're looking for, you can actually see that the prediction values have changed. Now, this is the binarized version of the predictions. So every prediction that was greater than 0.5 has been converted to a 1, and everything that's lower than 0.5 has been converted to a 0. So because the chosen calibration method was temperature scaling, we expect the contours, the binarized results to be exactly the same, because as I've been saying, temperature calibration does not affect accuracy. And that's exactly what we see on those two pictures. They look exactly the same. So just out of curiosity, let's look at what would have happened if we use isotonic regression instead. Now, on the graphs, you see temperature scaling on the left, you see isotonic regression on the right. Both graphs actually show a quite well-calibrated model. If you look at the top right of the graph, you can see slight differences. It's a little bit harder to say which of these calibration types is better without looking at the ECE, MC, and F1 scores holistically again. Now, the changes in the predictions are a little bit more obvious this time, if you ask me. So I'm just going to flick back and forth through the slides, and you can see that isotonic regression actually has, in my opinion, more significant changes than temperature scaling. But at the same time, what we are seeing is that the bright yellow predictions, so these are the bits where the model is really confident, they're being tamped down a bit. And even though it looks like the change is a lot more drastic, like if you look at the calibration curves, what it's doing is it's not drastically changing what the model is doing. It's just adjusting those confidences so that it matches up with your calibration line a lot better. Now let's look at another class, water body. So this is going to be things like the sea, ponds, or lakes. The class already started out quite well calibrated, but we can still improve things a bit by adding calibration. And in this case, the selected calibration method was plat scaling. So what I'm hoping to show you here is that you can get a difference in your binarized predictions if you use plat scaling. Now, because the model was already fairly well calibrated, the differences between the calibrated and uncalibrated model are not as obvious. So I am going to do a similar thing to what I did earlier, where I'm going to flick between the different predictions. And hopefully you can kind of see the differences. So for the predictions, especially if you look at the edges around the pool, you can see some bits where the confidences are being pulled down when you're using plat scaling. Now, the interesting bit is if you look at the binarized predictions on the middle and a bit to the left, as well as in the bottom right corner, you can see that the contours, right, the areas of the binarized predictions are shifting a bit depending on whether or not you have calibration applied. Right, so I'm just gonna wrap this up by talking about where we could go if we wanted to take this calibration system further. And there's sort of two categories that are divided into. You have the engineering improvements and you have the data science improvements. So some of the earlier experiments that I've done, sorry, these weren't actually earlier experiments. These were more recent experiments that I've done have suggested that we can get away with using less data in the calibration. And the reason, so by changing the way we sample how we get our calibration data set, we might be able to see some improvements. And the reason why I put this as an engineering problem is that, as I've mentioned, the calibration process is very input and output bound. So every time you can reduce the amount of data you're pulling, you can speed up the process by quite a bit. Now, there's some unevenness in how we distribute the workload between the different workers as well. So some of our labeled areas, they can have many classes labeled on them, while others only have a few. And what this leads to is the ETL step taking longer overall, since you have to wait for the slowest worker to complete before you can move on to the next step. So there's a way to do it more intelligently, where you try to make sure that you account for how many labeled classes you have in each image before you do the splitting. And hopefully that'll be able to bring down the dataset generation time. One thing which I also think would be interesting would be to make a trade-off between what I call the dataset resolution and the I/O performance. So currently we are storing the label prediction pairs, and the reason for that is, as you remember, we do histogram binning as part of the calibration. Storing the original labels and predictions as pairs gives us the flexibility to change how we perform the binning at any point in time that we want. So when we started work on calibration, we were looking at both linear and quantile binning. So linear binning is where your bins are determined by the minimum and maximum values, and everything that falls between those two values go into your bin. Whereas quantile binning basically says, how do I pick my minimum and maximum values of the bin so that each bin will have a similar number of predictions in there. So if we decide we want to lock in a specific binning strategy, we have the option of generating the histograms beforehand. Let's say I come up with 10,000 different bins. So it's not exactly the same as having your label prediction pairs, but you could still recombine them on the fly later on. And then from the data science perspective, there's definitely other calibration types we could be playing around with. In fact, the reason why we split the calibration up into the ETL and calibration stages was to make it easier to try different calibration types. And of course, there's some stability analysis we could do. I think it would be interesting to see whether all the calibration types are equally good at providing stability between different model releases. So that concludes my talk. Thank you all for coming and listening to me. I hope I've given you some insight into the systems we have at Nearmap that make calibrated models possible.
Yeah, no, thank you very much, Zeph. Towards the end, there was a bit of a latency, but I would love to ask you a few questions just to solidify sort of the underpinning of this presentation. So you're doing this procedure to ensure that you can calibrate a vision model that is the data product that is the basis of your entire company's value, right? That their value proposition is being able to provide accurate, timely models that are updated at regular intervals that reflect the reality. And as we've had dialogues in the past, it's not such a straightforward exercise because there's weather patterns, there are man-made structures, there are roads and roofs and trees, and sometimes things sort of overlap each other, um, and there's no straightforward answer to get complete accuracy, but you need to remain stable even as you upgrade your hardware, your software, your machine learning models. Everything needs to sort of be stable to a degree where it aligns with the previous results, because this has ramifications on insurance companies and other kinds of applications. Correct?
Yeah, so like I was saying, based on your downstream applications, right? You kind of want that stability, but also depending on how sophisticated your models are, it's not always a good idea to expect the customer to build in that recalibration kind of process into the model, right? It's a lot better if you tell them, hey, I gave you calibrated predictions, instead of expecting the downstream calculations, the downstream model that they're building on top of it to be able to handle uncalibrated results and essentially do the calibration themselves.
And the importance of that stability analysis is that, right? Like to ensure that despite having all these various methods for testing the same data set, that you can find that you're progressing in a very stable fashion, right?
Yeah. You don't want to have a model between generations suddenly say, hey, I was very confident that this is a roof and there's a tree over it. And then the next generation, all of a sudden, the confidence just drops a lot. And it's like, I'm very sure there's no roof there. And again, you could expect your downstream customers to deal with it. That's not a good idea, though, right?
Yeah, it's important to triple check your work, even if it means using all these different techniques, right?
Indeed, yeah.
Well, Seth, we're gonna have to pick this conversation up in a different event. I'd love to see how this, how the data travels from the device to the machine learning model, and how you how you annotate and enhance those models with human in the loop, because you need human judgment to ensure that you're tagging the right things, especially when there's edge cases or man-made structures. But I think we're gonna have to leave that one for another day.
Yeah. Well, that would be an interesting thing to discuss with people.
Thank you very much, Seth, and thank you everybody for watching. We'll catch you tomorrow. We'll have a series of panel discussions and a keynote by Michelle Yi. So, good night.